Now that you understand the techniques, let me share the design principles that make type-safe protocols successful in practice. These heuristics will help you avoid common pitfalls and create protocols that developers actually want to use. Model first, code second. The most critical steps happen when you write any code is to draw the state machine. This isn't optional documentation. It's essential design work that determines whether your protocol will be simple or complex, whether it will handle edge cases correctly, and whether developers will understand it intuitively. Start with paper on a whiteboard. Draw circles for state and arrows for transitions. Name every state clearly. Avoid generic names like state 1 or working. Use domain specific terminology that matches how users think about the problem. For a file processor, use states like closed, reading, writing, compressed, rather than abstract labels. Label every transition arrow with the method that triggers it. If multiple methods can trigger the same transition, that's a design smell. Consider whether those methods should be consolidated or whether you're missing a state. If you find transitions that seem to go backward in the protocol, examine whether that represents error recovery or whether your state model needs refinement. Look for states with no outgoing transitions. These might be terminal states, which is fine, or they might indicate incomplete design. Look for states with no incoming transitions. These might be unreachable, which suggests either missing functionality or unnecessary complexity. The state diagram then becomes your specification and your test plan. Every state should have a clear purpose. Every transition should be justified by user needs, and the overall flow should match how domain experts think about the process. Second is to hide constructors. One of the most effective ways to prevent protocol violation is to make it impossible to create objects in invalid states. Public constructors are dangerous because they often allow arbitrary initial states. Instead, force users through factory methods that guarantee valid starting conditions. Now, consider the difference between a new database connection, which takes a host, port, and an is connected Boolean parameter, and something which is a database connection dot connect with a host and a port. The constructor allows creating a connection with is connected true without actually performing the connection, leading to objects that lie about their state. The factory method, on the other hand, ensures that the initial state reflects reality. Static factory methods also provide better abstraction boundaries. They can handle complex initialization logic, perform validation, set up required dependencies, and choose appropriate implementations. The user gets a correctly configured object without needing to understand initialization details. For protocols with multiple valid starting states, provide separate factory methods for each. Transaction.begin for new transactions. Transaction.restore with a checkpoint for recovery scenarios. Each factory method guarantees its specific starting state. This pattern also helps with testing. Instead of trying to mock complex constructors, tests can use the same factory methods that production code uses, ensuring that test scenarios remain realistic. The third is to expose only intended transitions. Every public method in your protocol implementation should correspond to a deliberate state transition in your state machine diagrams. Methods that don't change state should be clearly identified as queries rather than commands. Methods that can be called in multiple states should have clear documentation about their behavior in each state. Avoid sink objects that provide every conceivable operation. Instead, design objects with clear, limited responsibilities that match their current state. A closed file shouldn't have read and write methods visible. It should only offer open. An uncommitted transaction shouldn't offer methods that assume persistence. This principle also applies to return values. Methods shouldn't return generic types like object or string, when more specific types should clarify the protocol. A method that returns a new state should return an interface representing that state, not a generic reference that could be in any state. Be particularly careful with convenience methods that seem to combine multiple state transitions. These can obscure the underlying protocol and make error recovery more difficult. If users need such convenience, provide them as optional helper methods that are clearly built on top of the fundamental protocol operations. Keep implementations transparent. The state tracking mechanisms we've discussed, phantom types, interface implementations, should be compile times tools that disappear at runtime. Users shouldn't pay performance costs for protocol safety, and the runtime behavior should be equivalent to a conventional implementation. This means avoiding runtime state checks wherever possible. Instead of storing a current state field and checking it in every method, use the type system to ensure that only valid methods are available in each state. The protocol enforcement happens at compile time through method visibility, not at runtime through conditional logic. When you do need runtime state, like for debugging, logging, or integration with external systems, make it observational rather than functional. Provide query methods like getStatus or isConnected that report the current state without affecting the protocol. These methods should never be required for correct protocol operations. Design your implementation so that method calls have the same performance characteristics regardless of protocol state. A commit operation should take the same time whether it's called through a typed protocol or through a traditional API. The type safety is a compile time benefit, not a runtime cost. And lastly, document the protocol. Even with type-safe protocols, documentations remains essential. Types capture the structure of valid interactions, but they don't explain the purpose, performance characteristics, or business rules underlying the protocol. Start your documentation with a state diagram. Most developers are visual learners, and a clear diagram helps them understand the big picture before diving into method signatures. Include typical usage examples that show the most common paths through the state machine. Explain the business rationale behind each state and transition. Why does compression need to happen before upload? What are the performance implications of keeping a connection open? When might a user want to roll back instead of commit? These explanations help developers make good decisions even when the type systems allows multiple valid choices. Document error recovery strategies. Type safe protocols prevent many errors, but they can't prevent network failures, disful conditions, or permission problems. Explain how users should handle these external failures and whether the protocol objects themselves remain usable afterwards. Include performance guidelines. Some state transitions might be expensive, some states might hold resources, some operations might block. Users need this information to design efficient systems, and the type system alone can't provide it.